Honors Algebra 2 Pre-Calc. We are still doing 2.5, which is inverse functions. So let's talk about inverses and composition of functions. So let g equal f inverse of x, meaning g is the inverse of x, right? Then f of g of x and g of, that's an open circle, I just fail miserably at drawing, g of f of x equals x, meaning they're the same. F of g and g of f are the same and they both equal x. Why? Well, an inverse is kind of like undo, right? So the f of x and g of x functions do exactly opposite things. Thus, they totally cancel out, leaving only the original input value, which was x. So a really simple, like oversimplified example of this. Let's say that f of x is x plus 5, meaning the f function's entire job is to add 5. F of x is x plus 5. If you plug a 2 in, it's 2 plus 5. If you plug a 20 in, it's 20 plus 5. If you plug an 8 in, it's 8 plus 5. That's f's whole job is to add 5. G of x's whole job is to subtract 5. So g of x equals x minus 5. Those are clearly exactly the opposite operation, right? One of these functions add 5, the other one takes it away, right? So it's sort of like if you're doing the dishes and you put clean dishes on the rack, and as soon as you put a clean dish on the rack, somebody in your family grabs the dish off to use it and makes it dirty, right? It's like you're adding a dish to the dish rack that you cleaned and somebody's taking it off immediately. That's undoing your work and making it dirty again, but you're also undoing their work by taking the dirty dish and making it clean, and then they make it dirty again, and whatever. So, again, exactly the opposite operations. If you did f of g, you'd get g plus 5, which is x minus 5 plus 5, which is just x. If you did g of f, you'd get f minus 5, which is x plus 5 minus 5, which is, again, just x. So that's a really oversimplified example, right? Because it's just using one operation, and you can clearly tell that they're inverses because they are taking that one operation and doing exactly the opposite thing. It'd sort of be like if one function multiplied things by 2 and the other function divided them by 2. Those are clearly exactly the opposite operation. So what we're going to do now is we're going to actually verify that functions are inverses using composition of functions. Now, I'm not going to make you do this very much, because I think it's tedious and a little bit frustrating. But if the book asks you to do this, if the book asks you to verify that two functions are inverses, what they're saying is find f of g and g of f and show that they're inverses. Now, let's say that the book doesn't use g. Let's say that they use f inverse. That can be a little bit tedious to use f inverse in notation, so you could just make a quick line that says let f inverse equal g. So let's do, this should be our E5, right? So we're going to show that, I'm going to give you two functions, f of x equals 2x minus 7, and g of x equals x plus 7 over 2 are inverses. What I'm going to do after this, just for a little bit of fun, is show you how I'm able to come up with inverses fairly quickly in my head for simple problems like this. Certainly not for the more complicated ones like we saw in E4, where I accidentally give you a function that was its own inverse. Okay, so in order to show that, right, or to verify that they are inverses, we need to do two things. We need to do f of g, and we need to do g of f, and we need to show that both of those equal x. So f of g is going to be f outside g, which means 2g minus 7, which is going to be 2 times g, which is x plus 7 over 2, minus a 7. Well, the 2's are going to cancel, and I'm going to get x plus 7 minus 7, which is totally just an x. So that one works. I'm going to do the same thing over here. G of f, sorry, I'll write it in the other notation, g of f should be f plus 7 over 2. Well, f was 2x minus 7 plus 7 all over 2. That's a 2x over 2. The 2's definitely cancel and give me an x. And so that's me showing that they're inverses. So now I'm going to give you a different one. Let's do P5. Same thing, right? Let's do f of x equals, let's do 4x plus 3. And we're going to do that g of x is an x minus 3 over 4, right? So you're going to go ahead and show that. You can pause me if you want. And then after that, I'm going to walk you through how I'm able to kind of quickly generate these, again, only for pretty simple examples. I'm going to go ahead and do f of g, g of f, and yes, the expectation is that you do both if you were asked to show this. So f of g is going to be f outside the g function, right, which is going to be 4g plus 3, right? So that's 4 times g, which is this whole ugly fraction, plus 3. Well, the fraction part cancels. I get x minus 3 plus 3, which is totally just an x, right? And when I do g of f, right, that's going to be f minus 3 all over 4, right, which is going to be a 4x plus 3 minus 3 all over 4. The plus 3 minus 3 adds to 0, right? And so I get 4x over 4, which is definitely just an x. So again, I showed that it works. So here's my kind of quick shortcut, and it works really well. It's not an official particular thing. It's just a cool, quick way to find an inverse logically. Now, if you were doing this on a test, I would need you to articulate why you did it, right? So anytime you take a mental leap that doesn't show any work on a test, you have to find a way to articulate why you did what you did. So here's my fun shortcut. I'm going to walk you through this one. So let's say from 4x plus 3, how did I mental math the inverse? And again, this is a shortcut that works really well with simple ones, but really not well with things like the ones that we saw that have x's on the bottom and the top. So here's how I mental math the inverse. I say to myself, what does f of x do? So specifically to x, right? Like, what does it do to x in order, right? So the first thing that happens to x is it gets multiplied by 4. And the second thing that happens to x after you multiply by 4 is you add 3. So then I say, how do I undo f? Well, it would be in exactly the reverse order, right? The same way as if you try and undo something on like a Microsoft Word document or on a Google document, right? That you undo backwards. If you realize you did something stupid like 3 things ago, you accidentally deleted a whole paragraph and you weren't paying attention, you have to undo, right, over and over and over till you get back to that mistake. So the first thing I would do is I would do the opposite of adding 3, which would be subtract 3. And the second thing I would do would be the opposite of multiplying by 4, which would be divide by 4. So if I do that to x, I get x minus 3 all over 4, which is totally what I got the inverse to be, right? So essentially I think to myself, if I were the x, what would be happening to me? In what order? Okay, cool. Now let me undo that backwards. And that works pretty much all the time, which is kind of cool. So let's do another composition of functions real quick. And again, I'm gonna go ahead and tell you that if I ask you to show that two functions are inverses, then it's safe to say that you know that they are inverses, right? So this, I believe, is example 6. Sometimes I'm bad at remembering how to count things. So f of x equals, all right, let's do 2x cubed minus 3, okay? And I'm going to go ahead and walk you through what the g of x is. I know that they're going to be inverses, but I'm going to ask you to show, so show that they are inverses, okay? Now I'm going to walk you through how I'm going to come up with this in my head. You don't have to do that, but it's kind of worth doing. I think to myself, okay, what's the first thing that's happening to the, so if I think to myself, what's f doing? 1, it's going to cube things. 2, it's going to multiply by 2. And 3, I'm going to subtract 3, right? So that means that what g must be doing is adding 3, dividing by 2, and then cube root. Right? Because I have to go in the opposite order to get rid of things. So basically, this is going to be an x plus 3 all over 2 inside a cube root. So when I ask you to check by composition of functions if two things are inverses, that's the idea. So let's do P6. I'm going to give you let's do an f of x that is, let's do x cubed over 4 plus 7. All right? And then g of x would be the cube root of a 4 times an x minus a 7. Cool. Should be right. Yep. All right. Cool. So let's show that these are inverses. Again, this is not a thing I'm going to make you do a whole bunch of times, but here we are. So I'm going to do f of g. I'm going to do g of f and show that they both come out to x's. So f of g is going to be 2g cubed minus 3, which is 2 cube root of x plus 3 over 2 quantity cubed minus 3, right? The cube is going to cancel the cube root. So I now have a 2 times an x plus 3 over 2 minus a 3. The 2's cancel. I get x plus 3 minus 3, which is totally just an x, right? If I do it in the other direction, g of f is going to be the cube root of f plus 3 all over 2, right? So that's going to be the cube root of 2x cubed minus 3 plus 3 all over 2. The minus 3 plus 3 sums to 0, so I get that this is the cube root of a 2x cubed over 2. The 2's cancel. The cube root of an x cubed just gives me my x, so they are inverses, right? Again, just worth showing that f and g are inverses if when you compose the functions, you get x back in both directions. All right, so I'm going to go ahead and do this one too. So f of g, g of f, right? And again, you can pause me if you don't want me to. So f of g is going to mean g cubed over 4 plus 7, right? Well, that's going to be the cube root of 4x minus 7 quantity cubed plus 7, and that whole bottom part was over 4. All right, so the cube is going to cancel the cube root, so I get a 4x minus 7 all over 4, which is going to cancel, and there's a plus 7 out here. So I have x minus 7 plus 7, which is just x. If I do g of f, I'm going to get cube root of 4 f minus 7, right? So that's going to be the cube root of a 4 times x cubed over 4 minus, or plus 7 minus 7, right? The plus 7 minus 7 goes to 0, so I get this is the cube root of a 4x cubed over 4. The 4's cancel. I get that this is the cube root of an x cubed, which is totally just an x. Okay, so that shows that my functions are inverses. Cool. Again, that trick, that shortcut for figuring out an inverse does not work anywhere near as well when you're talking about one of those that has a fraction with multiple x's. Cool. Okay, so let's talk about the horizontal line test. Let me grab the book so I get your page right, because sometimes I forget what page we're on. All right, so horizontal line test. So on page 120, right, so remember, so just a quick review, recall the vertical line test tells us if a curve is a function, okay? So as a quick review, right, this one would be a function, right, because the vertical lines only hit once, right? So this is a function, right? This one would be a function because each vertical line only hits once, function, okay? This one would not be a function, right? So, because these guys hit twice, so not a function. Something like a circle would not be a function, so not a function. Okay, so the vertical line test tells us if a curve is a function. The horizontal line test, which is on page 120, okay, page 120, the horizontal line test is the same test. So it's the same thing with the horizontal line, right? So it's just like the vertical line test. Tells if the inverse of the curve is a function. And this makes a ton of sense if you think about it, because what you're doing is you're switching the x's and y's in the graph. So the reason this wasn't a function is x occurs twice. Well, if you're trying to check if the inverse is a function, then you're not looking at the x's, you're looking at the y's because they'll become the x's. So, for example, the inverse is a function, okay, but on this one, the inverse is not a function, right? On this one, the inverse is a function, and on this one, the inverse is not a function, right? So an interesting thing here, if you want both the graph and its inverse to both be functions, then you need to use what's called one-to-one functions, which we talked about, right? So if we wanted to find a curve where both the inverse and the original are both functions, then it has to be a one-to-one function, 1x for 1y, 1y for 1x. This example, x cubed, is a one-to-one function. Neither of these are one-to-one functions, which is why, since this is not a one-to-one function, its inverse is not also a function, right? This one's not a function at all, but its inverse is, but that means it's not one-to-one, right? And this is not a function for either, right? So again, horizontal line test is exactly the same as the vertical line test. It just tells you if the inverse of something is a function. That's all. Cool. So all right. So let's talk about visually what an inverse looks like on a graph, okay? So And then we should also talk about things like how I think most of us probably think of a square root as the inverse of a square, which is true, but with a caveat or a restriction. Okay, so what do graphs of inverse functions look like? Okay, so the answer is, okay, so the answer, they are reflected across the line y equals x. Okay, so let me show you what I mean by that. Let's say that I have a function that is just a set of points. 1, 2, 3, 4, 5, 6, because I'm the most creative person on the planet. Oh, I'm going to regret that. Hang on. Let's make this a little bit easier. 1, 2, 3, 4, 5, 6. I want you to be able to see that the points are different. 4, 5, 6, my bad. All right. So what that means is based on what we know about inverses, right, F inverse should be the exact reverse points, right? It should be 4, 1, 5, 2, and 6, 3. So now let's look at that on a graph, and I'm terrible at drawing by hand, but you're gonna deal with it. It's gonna be fine. Okay. So let's look at this on a graph. I really only need quadrant 1 because all these points are in quadrant 1. 1, 2, 3, 4, 5. I usually make my 5 big so I can see it. 6. 1, 2, 3, 4, 5, 6. Great. Okay. So first off, the line y equals x, which I'm going to try and do in purple because most of my colorful markers are mostly dead. 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. Right? Close enough. Okay, this is the line where y equals x. Okay, and it goes into quadrant 3 as well. All right. So now let's plot f of x. So I'm going to plot f of x. My f of x points are 1, 4, right? 2, 5, and 3, 6, right? So these 3 points were all f. If I plot the other ones, right? 4, 1, 5, 2, and 6, 3, what I want you to notice is it's like I folded, so this is f inverse, these 3. It's like I folded this paper, right? Like when you were a little kid in kindergarten and you made butterflies, right? You put ink on paper and folded it in half, and then your parents told you that it was really awesome and you're totally an artist, and they were probably lying, but parents love you, so it's okay. So you fold it across, and you get these spots on this side. That's what happens when we graph inverses. Now you might say, okay, cool, that's what happened if you put a bunch of dots, but what happens if you put, let's say, lines? Okay, well, let's look at if I do this with a line, right? So let's go ahead and call g of x. Let's do 2x minus 4, okay? And g inverse of x, I know, is going to be an x plus 4 all over 2, which I'm probably going to write for graphing purposes as a 1/2 x plus 2, okay? So now let's graph these and see what that looks like, okay? So here I'm going to need some other quadrants because I have a -4 intercept. So 1, 2, 3, 4, 5 is big. 1, 2, 3, 4, 5 is big. 1, 2, 3, 4, 5 is big. 5 is big. Okay, cool. Let's go ahead and look at what these look like. So again, I'm going to go ahead in purple and put this y equals x. Okay, so 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Close enough. Okay, so this is my line that is sort of like a mirror, right? That's y equals x. All right, so now let's look at what these do. Okay, so I'm going to start with this -4 and then a slope of 2, which is going to be up 2, right 1, up 2, right 1, right, up 2, right 1, okay? So this graph is going to look something like this, okay? So this is my G graph, right? Okay, and again, forgive my terrible graphing. Now, my G inverse graph is going to start at +2 and have a slope of 1/2, which means up 1, right 2. So up 1, right 2, right? Or down 1 and left 2, right? Down 1 and left 2. Okay, so I'm going to go ahead and draw this guy. Now, again, ignore my terrible, terrible graphing, right? But what I want to show you is that if you were to fold over that purple line, if you fold the paper at that purple line, this line for G folds into this line for G inverse, right? That's my G inverse. And notice that at the spot where they hit the line, there's nowhere to fold, so it just stays on the line, right? Okay, so that's what inverse functions look like. Now, one of the things that your book hasn't dealt with a lot yet, because we don't do quadratics yet, really, is what happens if we need a function and we need to use its inverse function, but it doesn't actually have an inverse function because it fails the horizontal line test. So what we're going to do, again, this is a little bit beyond our scope. This is a bit of a skip to the next topic, just because it's worth integrating here while we're talking about it. Let's talk about x squared and the square root of x, which should, in theory, be inverses, but there's a problem, okay? So let's talk about x squared. We're going to see a lot of x squared graphs in math, right? Like, it's going to come up a lot. So let's talk about f of x equals x squared. Now, if we were to graph this, 1, 2, 1, 2, I'll go 3, 4. That's fine. 3, 4. Okay. 1, 2, 3, 4. That's plenty. Okay. So if I graph this, if I plug in some x values, now I would like eventually for you to know what an x squared graph looks like without actually having to plug in values, but let's just plug in some now. Let's start with x is 0. 0 squared is 0. 1 squared is a y value of 1. 2 squared is a y value of 4. And the same thing's going to happen on the negative side, because when we square things, we get positive. So we get this parabola shape, right? And we're going to spend a decent amount of time talking about x squareds in general, right? Okay, so that's my f of x. So we know, based on the horizontal line test, that the inverse function, the inverse is not a function, right? I think most of us understand that logically, so logic tells us that to undo a square with a square root, right? I think that's what logic tells us. So the interesting problem that we get is if you were to graph, so logic tells us that that essentially our inverse would be the square root of x. So is that our inverse? Well, let's think about what a square root of x would look like. So let's go ahead and put our line. Here's 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. Okay, so here's that line that we're going to reflect over every time we make an inverse. So that's y equals x, okay? So the question is the square root of x our inverse function, right? Well, if I plot some points for the square root of x, the square root of 0 is 0, the square root of 1 is 1. Now notice both of those fall on that dotted line, so that makes sense. But the square root of, now I'm not even going to bother with the square root of 2, because that's an irrational number, right? It's like 1.4 nonsense. I'm not going to bother with the square root of 3, which is 1.7 stuff. But I'm going to jump to the square root of 4 and know that that should be a 4, 2. So now I do this, and I say, well, that does look like this branch, right? So it looks like this arm folded over. But what happened to this half? Where did this half go? Well, it turns out that this half is actually what it looks like if you graph the negative square root of x. So the trick is that when we talk about x squared having an inverse function, we cheat. When functions don't have an inverse naturally, right, what we do is we give them a domain restriction. So when a function, like x squared or sine of x, when we get to trig functions, or cosine of x, doesn't have an inverse function, we cheat, and we give it a domain restriction. So what we say is that this chunk doesn't have an inverse function, but if we cheat and we only look at x values greater than 0, we do have an inverse function. So if we say something like f of x equals x squared for x values greater than or equal to 0, well, then we do have an inverse function. It's the square root of x, because this part does have an inverse function, right? Now, what's going to happen is essentially when we're solving squares, and this is one of the reasons why if you notice all your answers had cubes, not squares, because it was an easier thing to do than to address this issue. When you write a square root, to address this problem, you're going to actually have to write a plus or minus, right? So realistically, if I wanted to solve this, I would actually end up with two functions. I'd get like f inverse 1, which is the square root of x, and I'd say, oh, but it depends on the section I'm looking at. There's this other like f inverse 2 that we're going to call the negative square root of x, right? So the trick is that if you ever wanted to graph the inverse of a full x squared, you'd actually have to do it with two y values in your graph. You'd have to do y1 equals square root of x and y2 equals the negative square root of x. But that's the gist, is that when we have a function like x squared that comes up all the time, that we need to use all the time, and we need it to have an inverse function, we basically just cheat and say, hey, this whole thing doesn't have an inverse, but if I pretend this half doesn't exist, oh look, by setting a domain restriction, I say, cool, now I do have an inverse. And you're going to see that with sines and cosines and tangents and pretty much all the trig functions. So yeah, that's basically the deal. Oh, and hey, on page 120, your book actually does mention one-to-one functions. So I lied when I said they didn't mention it. They just barely mention it, but they do mention it on page 120. They mentioned that only one-to-one functions have both a function and an inverse function. So there you have it. So again, if something's not one-to-one, like this was not one-to-one, the math cheat is to restrict the domain to make the section you're looking at one-to-one. All right, that's it for 2.5. We'll go ahead and move forward in our next video.